Hello, this is video 3 on sequences. So one thing that I didn't mention last time when we went over geometric sequences were these powers. So if you remember from the syllabus, this class doesn't have a calculator, so you don't need one, and you shouldn't have one to do any of these things. You don't need one to do these things. So that being said, when we deal with geometric sequences where we have things raised to, the first power, second power, third power, and eventually to the n minus first power, you don't need to be able to calculate these things by hand. So the only powers that I'll expect you to be able to calculate in this course are first, second, and third. So normal to the first is there's no really calculation, but you need to be able to compute squares and cubes by hand. So let's look at what these squares and cubes are. So a sequence of squares just is a sequence of squares of numbers. So the most basic sequence you can have is 1, 2, 3, 4, 5, 6, corresponding to the first, second, third, fourth, fifth, and so on position. So the most basic sequence of squares is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, and so on, which correspond to the numbers 1, 4, 9, 16, 25, 36, and so on. So that's the most basic sequence of squares. It's 1 squared, 2 squared, 3 squared, and so on. So now let's look at cubes. So we have 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, and so on, which correspond to the numbers 1, 8, 27, 64, and 125, and so on. So you may not have known these squares or cubes off the top of your head, but eventually we'll work with sequences like this so much that you should just be able to recognize that these are cubes of numbers. So the sequences we're going to look at may not always look exactly like this. We are going to see shifted sequences of squares or cubes. So this is really similar to graphs in algebra, that you can have your normal graph of a parabola and you can shift it vertically or horizontally. We do something similar with shifting these sequences that we'll see in these examples. So let's go ahead and look at this example. So we're finding the nth term of the sequence 9, 16, 25, 36. So because we just wrote it, you should be able to look at this and identify that this is a sequence of squares. But if you hadn't just written it, well, the first thing you should try when identifying the pattern of a sequence is to see if it's arithmetic or geometric. That is, if you add a constant or multiply by a constant to get to the next term. So we see that to go from 9 to 16, we add 7. From 16 to 25, we add 9. From 25 to 36, we add 11. So we're not adding the same constant every time, but this is something I want to point out about sequences of squares, is that they do have this nice little trick of how to identify a sequence of squares, is that you add 3, and then 5, and then 7, and then 9, and then 11, and this pattern continues. So you add 3, 5, 7, 9, 11, 13, 15, 17, and so on to get to the next square. So whenever you're checking if something's an arithmetic sequence and you come across a pattern like this, where you add increasing odd numbers, you may be alerted to the fact that it's a sequence of squares. But regardless, it's not arithmetic. You can tell that it's not geometric just because there's nothing you can there's no whole number, no constant ratio you can multiply to get between these numbers. Okay, so we want to find the nth term. So we know it's a sequence of squares, but we don't know how to write the nth term. That is one thing I should mention up here, that in the sequence of squares, the nth term is just given by n squared. And in cubes, we have that the nth term is given by n cubed, right? So this just came because we took the numbers starting at 1, 2, 3, 4, and squared them and cubed them, where the number corresponded to the position in the sequence. So that's why these have such a simple nth term. So now we're going to shift them down here. So we're going to make a table like we did before. So we have an n and a term, and we're going to try and find pattern. So in this one, we are given the first 4 terms, where the first term is 9, second one is 16, third one is 25, and the fourth one is 36. So since we know that these are squares, we can just go ahead and write it out. So 9 is 3 squared, 16 is 4 squared, 25 is 5 squared, and 36 is 6 squared. So remember, we want to find something in terms of n where we have everything the same in our pattern except that n changes. So let's go ahead and try and find the pattern. So 3, let's see how that relates. So we have 3 squared, 4 squared, 5 squared, 6 squared. So the thing changing is our base, the number that's being squared. So let's see how the number that's being squared relates to the n position in the sequence. So how do 1, because 3 squared is the first term, how does 3 relate to 1? Well, we know that 3 is equal to 2, or 1 plus 2. So we can have 1 plus 2 is 3 squared. Okay, now let's see how our second term, 4 squared, relates to 2. Well, 4 is 2 plus 2, and we're squaring it. Similarly, for our third term, we are squaring 5, and 5 is 3 plus 2. And this continues. Again, 6 is 4 plus 2 squared. So we can generalize this pattern and get to our nth term. So we know that for each of these in our pattern, the thing changing is this number that we are adding to 2. And so that number exactly corresponds with the n position in our table. So we can write this general pattern as n plus 2 squared. So we can see how that relates to our general term of this sequence of squares, where we just had our nth term was n squared. And now we have our general nth term is n plus 2 squared. So this corresponds graphically to a horizontal shift, but this corresponds really to a shift in position. So I'm going to call this a shift in position, because what used to be in our third position, number 9, used to be in our third position, but now it went to our first position. What used to be in our fourth position up here in the general sequence now is in the second position. So it shifts the position 2. So what now, our first term is now what was in our third term compared to the original sequence. So this, we shifted the position. Okay, so now let's go to the other example. So the other example now has this sequence. So again, if we're not sure what a sequence is when we first look at it, we can first try to see if it's arithmetic or geometric. So again, 0 to 7, we add 7. 7 to 26, we add 21. Clearly not arithmetic because we don't add the same things. And it doesn't look like it's going to be geometric either, because if we multiply 0 by anything, we can never get 7 because we're just going to get 0. So that's not going to work either. So we can look at our sequence of squares and cubes to see if there's some relation here. So remember that our squares are 1, 4, 9, 16, 25, 36, so on. And our cubes are 1, 8, 27, 64, 1, 1, 125. So this doesn't exactly correspond with either of these sequences. So we can see if it at least looks similar to any of the numbers. So when we look at this 0 in the first term, well, we know that the squares and cubes both start with 1. So we can see that if we take the first term and subtract 1, we get 0. So when we look at 7, we see that 7, if we take this 8 and subtract 1, we get 7. If we look at this 26, well, that's just 27 minus 1. The 63 is just 64 minus 1. And so from this, we see that this sequence that we're given looks really similar to this sequence of cubes, but you just subtract 1 from all of the values. So we can make the table again. So we have n, and we have our term. So again, we're given 4 terms. We want to get down to the nth one. So our first term is 0, 7, 26, 63. And we are looking for a pattern. So we identified this with the sequence of cubes so that this first term is 1 cubed minus 1. Our second term is 2 cubed minus 1. Our third term is 3 cubed minus 1. Our fourth term is 4 cubed minus 1, where the only thing changing are, again, the space that we raised to our exponent corresponding exactly to the nth position. So we can write our general form as n cubed minus 1. So our nth term is n cubed minus 1. And so this one I'm going to call a shift in value, because we didn't shift on the n directly. We cubed the n and then shifted the value, whereas in this example, we changed what we squared. We didn't change what we cubed down here, we just shifted the value after we cubed it. Okay, so these are our examples of sequences of cubes and squares. So you should be able to recognize these over time. They're going to come up, and you should be able to identify eventually these different shifts. But that is all for our third video.